Alright, so today we're going to continue on algorithms and algorithm analysis. We left it off last time by talking about the 5-step process, and we started going through each one of those steps individually. Remember that we are on Piazza. If you have any questions, go ahead and post those to Piazza. By identifying the input, examples here, like if you've got a collection, then of course your input size is the size of the collection or the cardinality of that set. If you have an image where it might have multiple dimensions, right, you can simplify it so that you can assume that one dimension is larger than the other, and so you're only dealing with one variable, so that you don't have to worry about multiple, ultimately coming up with a function that is on multiple variables. But then we stopped off with a single integer, x. So if I've got a single integer, x, is there just one input? No, right? Numbers have a representation in a computer, and you need to be able to quantify that representation. So what's the input size of a number, x? Right? And we started off by giving you, I forget where we left off, but suppose that if I gave you a digit, a number of digits, right? Number of digits. If I said that you had one digit, what's the maximum number that you can represent there? 9. If I gave you 2 digits, you could represent up to 99. 3 digits, 999, ... Right? So if I gave you d digits, you could represent 10 to the d minus 1. Right? That's because we're base 10. So my question to you is, if I just give you x, right, and assume that x has a maximum value, how many digits is required to actually compute x, or to represent x, to write down x? So we have a clear idea of how to work from the left to the right. What if we wanted to work right to left? Right? So I want to compute x is equal to, let's just assume that it has a maximum value of 10 to the d minus 1. In other words, how many digits are required to represent x? Right? So all we need to do is solve for d, right? And I think we did that last time, or let's redo it. X plus 1, right, is equal to 10 to the d. Right? Now, how do I get rid of that 10 to solve for d? Log base 10 of each side, and that becomes simply d. Right? In other words, it requires about log base 10 x, and in this case I've just taken off that 1, just because you can take the floor, the ceiling, or something like this. If you just take the ceiling plus 1 or whatever, right, who cares? You're off by 1 digit. It doesn't really matter. Okay, so now that's base 10, and that's because the most fortunate of us still have all 10 fingers and 10 toes, right? So a computer doesn't have 10 fingers. It doesn't have any fingers. I mean, if you want to think of it as a finger, how many fingers does a computer have? 2. Well, 1, right? Technically 10 fingers, 10 toes for base 10, but a computer only has 2 toes, or 2 fingers, whatever you want to think. It's binary. Right? This is digital, right? It's base 10 digits. Binary is base 2. 2. So, same exercise as we did before. If I give you a number of bits, right? If I gave you only 1 bit, you could represent 1, which is equal to 1. And I'll write it as base 2 here. Right? So this is the max number. If I gave you 2 bits, you could write down 1, 1. Right? And in binary, that's going to be, anybody know binary? 3. Right? If I gave you 3 bits, 1, 1, 1, again, base 2, that's going to be 7. Right? ... If I gave you b bits instead of d digits, right? What's the maximum number that you could represent? Well, 1, 1, 1, ... 1, 1. There are going to be b of these bits here, all set to 1. And what's that going to be? 2 to the b minus 1, right? Because it's base 2. Right? It's the exact same thing as before, right? Right here. but it's a different base system too. Okay? So how many bits are required to represent x? All we have to do is the same math as over here, right? The same, this same math, but the only difference is going to be what? Log base 2, exactly. Log base 2, and I'll go ahead and say that it's about log base 2 of x, right? In other words, the number of bits required to represent x in a computer. Now, does it really matter if we work on a piece of paper or a digital piece of paper like I'm doing right now, or a computer, or if we meet aliens 100 years from now and they have 16 digits and they have 16 fingers, and so they do base 16, or they have only 3 or something like that, and they do base 3. Do we really have to worry about that? In other words, are their computers faster because they got more fingers? No, why? Log base b can always be converted into anything else. How? Log base a of x all over log base a of b. This here is just a constant. In other words, you can change it from any base system to any other base system, and the only difference is some constant sitting out front. And remember, in step 5, eventually when we get there, we're going to be throwing out lower order terms. We're going to be throwing out constants, so who cares? Right? I think we briefly talked offline about what about other base systems, like, say, the natural log is log base e. Why is that natural? How in the hell is e 2.71 dot dot dot? How is that a natural log, at least according to mathematicians? It's if you take the first derivative of e to the x, you get e to the x with a 1 out front, right? And nobody ever writes the 1, and that's why they consider it natural. Okay. All right. So numbers have a representation on a computer or on a piece of paper. The input size of a number is the number of bits used to represent that number. So in other words, log base 2 of n. Right? But we're self-respecting computer scientists, right? All of our bases will be base 2, right? Why? Because it doesn't matter. You convert your base 10 system into my base 2 system so I can run it on a computer. You take your so-called natural log base system, which you can't even write down because there's no such thing as 2.75 numbers. But you can always convert that to my base system where I can actually write it down. Right? So all of our bases will be implicitly base 2, and we simply write log of n, or log of x, I should say. I'm going to change both of those to x because n is usually used as our input size, so n will be equal to log base 2 of x. That's our input size. Okay, and that does come up more than you probably think all the time. You know, if somebody will come up with a naive way of looking at integer factorization or primality testing and say, oh, it's just a simple for loop, right? Well, if you analyze that simple for loop with respect to the real input size, the number of bits required to represent that number, then you find out really quickly that these so-called efficient algorithms are not actually efficient, they're exponential. And I've got an example of that on the pre-prepared videos that I'll go ahead and skip for brevity and time here. All right? Analysis. Right, so this is step 4. Remember that it's a 5-step process. Identify the input. We need to step 3 here. We identify the elementary operation. So elementary operation. There we go. I'll snap to that. Okay. So ultimately, we only want to focus on one operation in an algorithm. An algorithm might be doing a lot of things. It might be doing a comparison, it might be doing a division, it might be doing a summation, it might be doing a whole bunch of different things. We don't want to consider 10 different operations. We want to focus down onto one operation because that's going to quantify all the rest of the work, right? And when you do that, of course, you generally want to choose the most expensive or most common or common or most relevant operation. Right? Again, it might be doing a division over there, and it might be doing a plus over there, but the plus is actually the addition is actually inside this loop. And so even though generally a division is more expensive than like say an addition, the addition is being performed way more times because it's being done inside of a loop. That's going to be way more common, and overall, if it depends on your input size, it's going to be way more expensive, right? So generally, you also don't include things that are necessary for the algorithmic control structures, right? So you generally also exclude operations that are necessary for the control structures of the algorithm. Right? So consider a typical for loop. For int I equals 0, I is less than n, I plus plus. That simple for loop there has an initialization. That's some cost, right? It has an addition, I plus plus, right? It also has a comparison. While I is less than n, that's computed every single time in the for loop. Ignore all that stuff. That stuff is necessary to the control structure of the algorithm itself. Obviously, you're doing something inside that loop. So whatever you're doing inside that loop is probably a lot more relevant than just the simple iterator variable that you're incrementing and checking every single time. Not only that, but if you do want to really consider the operation and the cost of your actual for loop, right? Whatever operation you've got inside your loop, that's going to be proportional. All this other cost up here is proportional to that cost. If your loop goes n times, sure, you're doing n comparisons, you're doing n additions. But if you're doing something way more expensive inside, you're also doing n of those operations. So it's just simply n plus n plus n, right? And it's 3n, right? And 3 becomes a constant sitting out front that we throw away in step 5. Okay? Some examples, right? Comparisons. If you've got a searching or sorting algorithm, which is what we're going to do next, you'll probably want to focus on those comparisons because that's are these things in order? Yes or no? If they're in order, then leave them alone. If they're not in order, then swap them or something like that. Right? You have arithmetic operations, right? Operations, yeah, there we go. For example, additions and subtractions, or multiplications, divisions. Right? And here there are lots of arithmetic operations. You could group them all together and perform an analysis, or you could focus on one or the other. I put a slash between, I grouped additions and subtractions, and I grouped multiplications and divisions. Why did I do that? Are additions and subtractions any different? No. What's a subtraction? It's an addition of a negative number, right? Are multiplications and divisions any different from each other? Nope. What's a division? It's a multiple of the reciprocal, or the inverse, right? Much better word, good. The reciprocal is the grade school word. The inverse is the real algebra word, right? Oh, okay, yeah, that too. But which one, among these two groups, which one is clearly more expensive? Multiplications and divisions, or additions and subtractions? Multiplications and divisions. Because multiplications can actually be done through iterated addition. 10 times 5, add 10 5 times. Right. Similar, and then of course if you're doing 1 over 5 times, or 5 divided by 10, then you can take the reciprocal and do almost the exact same thing. But again, in general, you need to make a judicious choice there. If your algorithm does 1 multiplication, but it does 50 additions because they're on an input size of 50 because it's done inside of a loop, that's probably way more relevant, right? That's what's going to grow and blow up as your input size grows. You also have, say, linked lists, right? Traversing nodes in a linked list, right? That could also be considered an elementary operation, and that's what we considered at the very top when we started. That searching through a linked list cost us something. What did it cost? Well, we had to go from one node to the next node to the next node to the next node, and we did that over and over again, and the naive painter never took his paint can with him, so that ended up being way more the really expensive operation, right? And it really, again, it depends on the nature of the algorithm. I can only give you a couple of examples, and we're going to work through several examples today and next week. Choosing these things, there's not necessarily only one right choice. There could be a couple of choices. One, your choice of elementary operation, your choice of input, your choice of input size could lead to a different analysis of the algorithm. And that's perfectly fine as long as it's reasonable, right? So the fourth step is the actual analysis. You need to analyze how many times the elementary operation is executed with respect to the input size, n. Right? That is, you come up with a resource function. You derive, or I don't even want to say derive, you come up with a resource function, right? A function that looks something like this. F is going to map, and I think I've got full LaTeX here. Yeah, it's going to map natural numbers to positive real numbers. There we go. Right. Oh, because I misspelled it. Okay, I like that. All right. So F, in fact, I'm not even going to call it F. I'm going to call it T for time. Time resource, if you want to think of it that way. If you want to think about it as memory, maybe you call your function M instead. N is the natural numbers. 0, 1, 2, 3, 4, 5. Right? Why do we restrict the domain of this function over here to natural numbers? Because it's capturing an input size. Can you have a negatively sized input? Doesn't make any sense. Can you have an input size of 3.5 elements? No. Right? So we're restricting our domain consideration input sizes, right? Input sizes to R plus. R is real numbers, but positive real numbers. So in other words, no negative numbers. Why do we exclude negative numbers? Think about this as time. For an input size of 50, it takes X time or T time to actually execute. Have you ever heard of a computer that takes negative time to compute? So you started the computer now, and then the result was actually, 10 minutes ago. That's time travel right there. that would be a huge breakthrough. Like, yes, definitely, let's do that. That would be some quantum mechanics kind of stuff where you're transmitting data back in time, right? What was the movie that was just released about reversal time travel? Tenet? Yeah, there we go. Very, very good. You got to watch it a couple of times, though, right? Input sizes to a resource measure, such as time, right? There we go. And of course, the resource measure can't be negative because the computer doesn't pay you to run itself, right? It consumes power. It takes time. It requires memory, right? And those resources cannot be negative. If you ever came up with an algorithm that gave you negative resources, for example, your bit mining now not only does bit mining, but it also generates power for you. Wow, cool. Let's do that. Maybe the 390s do that, I don't know. So it may require some art, right? Some summations or other calculations, right? Finding closed form solutions, or even super advanced math, right? An analysis of an algorithm could require you to know advanced field theory or something like that. We're not going to get into anything that complicated here, right? But in general, you want to assume the worst case scenario. Right? You want to provide an upper bound on the worst running time or other resource that the algorithm could cost you. Right? And we're going to see exactly what I mean by this in our first example. In fact, we've probably seen this example before. Right? So, go back over here. All right, and create a new one here. So we've all seen linear search before. In fact, we just did linear search in our linked list and array-based list demonstrations. But let's go ahead and write the pseudocode for it, for linear search. Right? Now, just to give ourselves some more practice here. Now, remember, let me see. Let me check, see if we have any questions so far. Nope. Okay, so remember that with pseudocode, we have to be general, we have to be generic. And also it's best practice to label your input and label your output. Right? So my input in this case is going to be a collection that I'm searching through, the haystack, and a key, the needle that I'm looking for. So a collection, and I'll give that collection a name. A1, A2, ... and all of the elements a name. And implicitly encode the size of my input by using the n variable right here. Okay. Note also that I am going with 1 indexing because that's more traditional in mathematics. 0 indexing is a computer science thing. And we are all self-respecting computer scientists, except when it comes to pseudocode. We like the use of mathematics. Right? In fact, computer science is computer science engineering. Nope. Computer engineering is engineering to a point. It's as long as you stick in the mechatronics, like the robotics or the electrical engineering kind of sphere, right? Because it's a physical. It's engineering on a physical system. But computer science itself is not a science. It's not an engineering discipline. Is it a science, even though we call it a science? Not really, right? Because there's not. It's not studying the natural world, the natural phenomenon. It's something completely different. And so a lot of people try to pigeonhole it into something that is well established, like engineering, or science, or something like that. Traditionally, however, it's math, right? At the heart of everything is math. Right? That's a branch of mathematics. So a collection, A, and a key. Okay. And what we'll do is we'll output an element. Note here I'm not being specific. An element, there could be multiple values that match the key K, but I'm saying an element, A sub I, such that A sub I is equal to the key. Okay? All right. So it's pretty straightforward, right? For each element, A sub I, in the collection A, get rid of that. If A sub I is equal to the key K, we'll output A sub I. And remember that I'm using those vertical lines there to denote code blocks as well as indentation. I'm not using colons here. I almost did. That would be very Python-esque. I'm not using opening and closing curly brackets. That would be very C-style syntax. I'm using something that you can't even get by regularly typing with the QWERTY keyboard. Right? What happens if we don't find what we're looking for? Yeah, that's a design question on do we return null? Do we return -1? Do we throw an exception? In this case, I'm going to return something mathematical. Output phi. Phi is often a placeholder for null or for nothing or something like that. Phi is phi. It's nothing. Right? Okay. That is pretty good. Now what we need to do is go through our process, our 5-step process. We haven't gotten to step 5 yet. That's all right. I'm saving that for after we've got a few examples under our belt. So number 1, what's the input? Well, again, that's the easy part if you've written good pseudocode. It's already encoded up here as part of the input, right? However, we do have one of those corner cases that we need to think about. We've actually got 2 inputs here. We've got the collection and we've got the key. Which one do you think is most relevant? The collection. Why? Because it has n elements and it can grow. With this algorithm, you will only ever have 1 key. So, we're going to choose to use the collection. The collection A. 2. What's the input size? N, the size of the collection, right? And again, we encoded that with good pseudocode up here. Okay. 3, what's the elementary operation? So before we answer that question, here's another trick when writing pseudocode. Oftentimes, you'll want to make reference to a line number. So let's go back and number our lines. 1, 2, 3, 4. Okay? All right, so what's the elementary operation here? The comparison on line 2. This one right here. I like that. Of course, again, this for loop is going to have implicitly, if you actually put this onto a computer, it's going to have an initialization, a continuation condition. There's going to be a comparison there, right? If I go for I equals 0, I is less than n, right? This right here is a comparison that would appear in this for loop up here. Why don't we count it? Because it's necessary for the control structure of the algorithm. You're doing something inside this loop, presumably, otherwise why did you write the loop? And that work is what's relevant to the actual algorithm, not the control structures, okay? All right, so I like that. The comparison on line 2, right? 4, how many times is it executed with respect to the input size? How many times is it executed with respect to WRT n? Oh, I like that. You're thinking about it depends, right? It depends. ... Let's think about, so I already said that we probably want to think about worst case scenario, but let's be devil's advocate here, right? Best case. Go away. Best case. I thought I turned off notifications. MLB doesn't care about me turning off my notifications, apparently. So what's the best case scenario? 1. Why? 1 comparison. And you get lucky, right? You find it at the first place you look for. You find that A1 is equal to the key. Right? I like that, best case. What about worst case scenario? N comparisons. Good. A of n, it's the last place you looked, right? Or what? No such value. Okay. In either one of those cases, you would end up making n comparisons. Why? Because if there are n elements in the list, then you have to look at the first one, the second one, the third one, ... all the way to the last one. Okay? Now, you could look at something in between these two, right? What about the average case? N over, say, what? Over 2? I like that. How did you come up with that, though? Well, one naive way of doing it is take the best case and the worst case and average them together, right? And you get about n divided by 2. However, that's the naive way of looking at it. The actual amortized analysis would require you to define a probability distribution on the successful search for each element, and then how many comparisons it took for you to take that element, sum them all up, take an average, and then of course the probability of an unsuccessful one, blah, 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 blah. And guess what? You come up with the exact same answer. N divided by 2, approximately, right? But which one are we concerned with? The worst case scenario. In fact, the worst case scenario and the average case, are they much different? There's just, yeah, they're both linear functions, which is why we call it linear search. The best case scenario, you cannot always be that optimistic, right? You could, you could take a look at, a compromise and look at the average case scenario, but ultimately it's going to be some linear function, right? Yes, this is probably a much better gauge of performance in practice, but it's asymptotically, when we get to step 5, it's no better than the worst case scenario, right? And the worst case scenario is what we're really concerned with, because, yeah, okay, that's on average, but I want to know, what is my absolute worst case that I'm going to have to wait and sit for this algorithm to actually compute and execute, right? If the average case was 10 minutes, but the worst case scenario was, 50 million years, right? That's concerning, right? All right, so worst case scenario is going to be n, right? Oops. So this is going to be our answer right here. There are n comparisons. In other words, we came up with a function. F of n is equal to n. And that's a linear function. Ultimately, in step 5, we're going to say that n is order n. That's big O analysis, big O, right? And this is the easy, you don't have to even know what the definition of it is in order to understand what I'm writing here. That its order is n, it's a linear function. Right? We'll get to that later on here. Otherwise, what I want to do is I want to look at another example. We've probably seen this, this algorithm before, selection sort. Remind me, though, how it works. So, 8, 7, 4, 3, 2, 5. Right? I want to sort that. How does selection sort do it? It goes through and finds the minimum element. So 8 is my minimum. Oh, 7, I found something new. Something a little smaller. 7. 4, oh, that's even smaller. There's my new minimum. 3, that's even smaller. I didn't mean to write it like this, but I meant to interleave a lot more. And then finally 2. Oh, 2 is the absolute minimum. 5 is bigger, so 2 must be the actual minimum. So what we're going to do is swap 8 and 8 and 2. We ended up swapping those two. Now we continue with the rest. With the rest of the list. We go through and we find the minimum. The minimum now is 3, and so we end up with 7 and 3. Then we go through and the rest of it. 4 ends up being our minimum. We swap it with itself, and it stays right there. We go through another time, 7, 8, and 5. We find that 5 is our minimum, and we end up swapping 7 and 5. And then the last iteration, we end up swapping 7 and 8. And now it's sorted, right? That's selection sort. That's how it works. Okay? Let's write the code to do it, the pseudocode to do it. I'm going to clearly label my input. And in this case, there's only one of them, right? A collection. A, consisting of A1 through AN. Okay? And our output here is going to be A sorted. Are we passing this by value so that we give you a sorted copy? Are we passing this by reference so that we actually change what you gave us? I don't know. That's a implementation question, not a pseudocode implementation question. Yeah.
Should we still specify like a sorted in ascending order, or is it just something that says sorted?
I keep it general. Ascending, descending. One is just the reverse of the other. When you actually go to program this, you give it one comparator, or you give it the reversed comparator, right? So who cares? Ultimately, it's going to be the same algorithm, just that instead of greater than, it's going to be less than when you do your comparisons. Right? And ultimately, that'll be a comparator anyway, and so it's just a function call. All right. Does anybody remember? So, obviously, I did that process over and over again. I started at the beginning, and then I took the minimum of all of them. Then, once that one was in place, I went through the rest of them, elements 2 through n, and I found the minimum among those, and I put that at the beginning. Then on the next iteration, I did 3 through n, right? So I'm going to go ahead and write from I, running from 1 up to some value here, right? And we'll come back and fill in that blank. On the first iteration, I consider 1 through n. On the second iteration, I consider 2 through n, 3 through n, 4 through n, right? And what here I'm going to do here is I'm going to find the minimum element among a sub I through a sub n. I am putting in a comment here, right? You could put comments in pseudocode. Right? You could actually just make this your pseudocode, except that it kind of hides the complexity, right? If you were to describe how do you find the minimum, well, you just find it. Is that at all satisfying? No. So let's actually describe that process, right? So the min element here, a sub min, is going to end up being, where do I start? A sub I. And then I'll have another for loop. For j, because I've already used I, running from I plus 1 through n, if I find something that is less, a sub j is less than a sub min, then I found something less and I need to update a sub min. All right? Now, why did I start at I plus 1 on that second for loop? Yeah, you don't compare a sub I to itself, right? I'm assuming that this is my minimum, and then I'm going through the rest of the elements to see if I can find something smaller. Okay? Okay. Once I've found the minimum, I swap. Oops, I didn't mean to do that. I swap a sub I and a sub min. Nice use of plain English there. If you were to actually do this, you'd have to have at least 3 lines maybe. A temporary variable to take one, then you put one into the other, and then you put the temporary variable back into the original variable, or the second variable, right? That's details that don't matter, right? Just swap them, okay? And at that point, I am done. Now let's go back and fix this fill in the blank here. So on the first iteration, I consider 1 through n. Second iteration, 2 through n, 3 through n, 4 through n, dot, 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 n minus 1 through n, right? I have to find the minimum of 2 elements. But when I've got only 1 element left, guess what? It's where it needs to be, right? So I'm only going to go up to n minus 1. Keeping in mind here, remember, that these are all 1 indexed. If I were to do this on an actual computer, of course, 0 through n minus 1, all of these numbers would be off by 1. Right? So when you're translating pseudocode over into real code, you do have to make those considerations. Okay? So 1 and 2, that should be easy. Right? The input is the collection, and its size is n. What's our elementary operation, though? Again, let's go ahead and number these. 1, I will number the comment. 2, 3, 4, 5, 6, and 7. So what's our elementary operation? Lots of stuff going on here, right? Let's start from the top. Should I consider anything in the for loop itself? No, because that's necessary for the control structure of the algorithm, right? Don't consider the comment. I'd be really worried if somebody seriously thought that, oh yeah, that comment should be the elementary operation, right? What about my initialization here? My assignment? Maybe, we'll come back to that. And then I've got another loop, a nested loop, a loop within a loop. And I'm doing work within that loop. Immediately I say, no, not that then, because I've got more common operations down here. This is only done once for every iteration of the outer for loop. Whatever's being done in here is way more common. Right? So I've got a comparison and I've got an assignment. Probably the comparison. Is the assignment always executed? Nope, it depends on the outcome of your comparison right there. So I will say the comparison on line 5. 4, analysis. Right? How many times is it executed with respect to the input size? Okay, we're going to have to work in to out. In other words, I'm going to start at this line and focus only on line 5. Ignore everything else. Only focus on this block right here. How many times is the comparison executed on line 5? Just once, right? If you ignore everything else, right? So 1, and this is line 5. All right, now let's expand our consideration here. Line 5, the block at line 5, is actually part of the for loop on line 4. So how many times is line 5 executed with respect to line 4? Well, it's executed when j is I plus 1, I plus 2, I plus 3, dot, 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 n. Yeah, n minus I, algebra. Let's just go ahead and set up a summation and then worry about the algebra later. The summation runs from j, I plus 1, up to n. Right? You're doing I plus 1, I plus 2, I plus 3, I plus 4, right? You're doing one comparison, one comparison, one comparison, one comparison. You're summing up all of those comparisons. Now that means that we can expand out this block of code to the outer for loop here. Same trick. I don't want to have to worry about the algebra just yet. Right? Let's just go ahead and set up a summation and we'll solve it later. This outer summation runs from I being 1 up to n minus 1. And you can put a parentheses here if you want to, but usually people don't because that's the default way of looking at summations. Summations of sums, sums of summations, right? You're looking inward, outward, okay? Now all we have to do is solve this summation, right? So, I don't know if I can cut and paste that, but that's all right. Let's go ahead and reset this summation up. What was it? I running from 1 up to n minus 1. J running from I plus 1 up to n, and 1 inside. Okay. If you're not good at solving summations, go ahead and use a solver, right? Or do some practice so that you can get more practice with it. First of all, let's focus on this inner summation here. Again, this was 1 plus 1 plus 1 plus 1 dot 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 plus 1. How many times? Well, if I associate an index with each one of these, then I can say that this one was done at I plus 1, this one was done at I plus 2, this one was done at I plus 3, dot dot dot, this one was done at n. So in terms of n and I, how many ones are there? If I were to expand it out this way and say that I started at 1 instead, 1, 2, dot, 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 stop short at I, now how many ones are there? I, up to this point, I, right? How many are there total? N. So how many must there be here? n minus I. There. Okay. Now all we need to do is solve the rest of it. Summation of sums is equal to the sum of summations. This is a sum. It just happens to be a sum of a negative number, right? So let's expand this out. This is actually two sums. Sum of I running from 1 up to n minus 1 of n minus sum of I running from 1 up to n minus 1 of I. You can just split that up into two summations. This one should be super easy. N plus n plus n plus n, how many times? We start at 1, we go up to n minus 1. So it should be, well, n squared, let's go ahead and keep it in exact terms for now, right? Right? N plus n plus n plus n, n minus 1 times, therefore n times n minus 1. Minus. What about that guy right there? Does that ring any bells? 1 plus 2 plus 3 plus 4 dot 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 plus n minus 1. What's that guy's name again? That guy. That guy.
Guy's formula.
Equals Gauss.
Okay.
Gauss's formula, summation of natural numbers. Remember, all you have to remember is little tiny Gauss given busy work to sum up 1 to 100, and he came up with a formula. What was that formula? I don't know, I'm not Gauss. I go look it up, right? That's why we don't require memorization. But it is n times n plus 1 all over 2, but we stop short in this case, so it's going to end up being n minus 1 times n plus 1 minus 1, so that those cancel out, all over 2. Right? Awesome. If you can look really closely and squint here, you can see that this thing is the same as the numerator over here. And so subtracting off 1/2 of the original, what do you get? 1/2 of the original. Right? Or, if you want to expand it out, 1/2 n squared minus n 1/2 n. There. All right. What's the most important term here, do you think? N squared. Right? This n squared term is the most important. This lower order term, who cares? This constant sitting out front, who cares? Right? Upgrade your hardware and that's a different constant. So we say that this is order n squared. It is quadratic. Again, that's step 5. We need to define those things before we get into it. Right? I thought I would need it, but there is a nice selection sort, all nicely typeset in LaTeX. Right? Let's do one more example. Yeah, we've got plenty of time. Let's do a different sorting algorithm, one that you may not have seen before. This sorting algorithm is called Insertion Sort. 2, 3, 4, 7, 1, 5. All right, there's my list. So the idea here is that you insert something where it needs to be by shifting it down. So what I mean by that is we're going to start over here with just considering this thing right here. Now, by definition, and we're going to ignore everything else. By definition, a collection or a list of size 1 is sorted, right? If you, I can physically cover it up by hand over here, but I can't show you on the screen. That's why I'm crossing it out. If you just crossed, let's say, if you got rid of all this stuff, I'm not going to do that because I don't know how to undo on this thing. If we got rid of all this stuff and we just had 2, do you need to sort it? No, it's sorted. So what we're going to do is we're going to start at this one. Now, ignore everything else and just look at this array. Is it sorted? Yeah, because so you don't need to shift 4 down anymore, right? So, similar, 2, 4, 7. That's in order as well. So I'm going to go over to the next element. Oh, consider this now. Is 5 where it needs to be? No. Where does it need to be? Over here. So what does the operation look like? We start at 5 and say, compare it to the one immediately to its left. We find out that it's out of order, so what we're going to do is we're going to put, actually what we do is we put 5 into a temporary variable up here, okay? That makes room, right? Let's see. That makes room to shift things up. And then eventually we'll have enough room to insert 5 where it needs to be. So because it's over here in this temporary variable. We're comparing, let's see, we're comparing 5 and 7. We find that they're out of order, so we shift 7 up. And we eventually come to this. Right. There. Now there's a gap here. We continue. 5 and 4. Are they, 5 would go after 4, so what do? We simply just put it there. We insert 5 where it needs to be. Okay? At this point, there's our sorted array or list. Right? And we continue with the rest of it. 1 is our next element over here. In fact, I'm going to highlight it in red, right, because that's our, and then put it up here, t equals 1. Right? And now we get rid of it because we now have room to shift stuff up. Okay? We compare 1 and 7 and find that they're out of order, so we shift 7 over. Oops. I want to go back to my other color, 7. Right, we shift 7 over. We look at 1 and 5, and we see that the 1 would go before it, so we shift 5 up. We shift 4 over. We shift 1 over. And finally, we've got something that looks like 1, 2, 4, 5, 7. Right? And we put 1 where it needs to be. Right? We've inserted it where it needs to be. Likewise, we do the same thing on the last iteration for 3 here. 7 will be shifted up, 5 will be shifted up, 4 will be shifted up, and then we end up inserting 3 right here for the full sorted list or sorted array. Okay. Now we have enough time that we can kind of we can try to derive this. Otherwise, I've got it already pre-prepared here. So here's here's our insertion sort algorithm. Our input and output will be the same. A collection, A1 through AN. Our output will be A sorted. And I don't think I ever actually put that out, right? Output A, right? But implicitly it was there. Okay. All right, A sorted. So help me codify this. Remember when we began, did we start at the first element? The first element was already sorted. So we did this process over and over and over again with a for loop, but we only really started at the second one. Right? So for I starting at 2 and going up to something, I don't know yet, what we're going to do is we're going to put into a temporary variable a sub I. Right? That's what I did over here when I put something into a temporary variable. Okay? Now what? I'm going to look at all the other elements and shift them over as long as they are greater than or equal to maybe, or greater than or strictly greater than the temporary variable. Shift things over, shift things over, shift things over. Okay? To do that, I need another index variable here, j. Where am I going to start looking at things? When I did 3, there's a sub I. I'm looking at a sub I minus 1. So j will start at I minus 1. And it'll go down. Right? So I'm not going to but it doesn't always go all the way down, does it? In fact, here, if 3 will end up getting inserted right here, right? So I'm going to stop short when the temporary variable here is where it needs to be. So that tells me that maybe I want a while loop, while some condition. All right? So let's think about this. And I'll do it on scratch work over here. We've got our temporary variable here, and we've got our a sub j. Right? And I'm going to compare my temporary variable and a sub j. If the temporary variable is less than a sub j, then what should I do? So move a sub j to where? Remember, we're not moving things down. We're moving it like to the right. Right? I would consider this down and this up, just because it's left to right. Right? So move a sub j where? But let's go with left and right instead. To the right. And where is that going to be? If I move a sub j to a sub j plus 1. All right? So while t is less than a sub j, I will say that a sub j plus 1 is equal to a sub j. Right? I'm just moving it up, because remember, by putting it into this temporary variable over here, I've freed up space for it. Right? I need to set myself up for the next while loop. So what should I do with j? Remember, it's going to go down. So j minus minus. If you want to be technical, that's not all programming languages have the compound or the iterator operator like that, and so you could say that j will take on the value of j minus 1. You're getting too pedantic there. Minus minus is just fine. If your language doesn't support that, your language sucks. All right, I left myself some room here. Right? Why did I leave myself some room? What happens when we put 1 all the way back? Say that there's 0 here. Right? What happens when we shift it all the way down here? Should we keep going? Nope. We want to stop short. While j is greater than 1, right? Because once j hits 1, that's it. You're at the end. Right? You've gone all the way to the end, and you should not be going any further. So and there we go. There. And that's it. So where do we stop? If everything has been inserted where it needs, inserted 1 through n minus 1, that last guy still needs to possibly be inserted where he needs to be. So I go all the way up to n here. And if I did this correctly, it should look something like this. Very nicely typeset here. And in fact, we start at 2, we go up to n, right? Did I get it right? Yeah. I use t instead of x for my temporary variable. I don't know why I did x here, but whatever. And then I start at j is I. Yep. I started at I minus 1. That's because I go. I put j minus 1 into j and then decrement I. I'm just off by 1. Right. It both. So again, let's go through line by line. Anything in the for loop? Nope, that's necessary for the control structure of the algorithm. 2 assignments. There's a while loop down here, right? So we're repeating something else down there. This comparison, that's just making sure that you don't fall off the edge of your array. That's necessary for the control structure of the algorithm. There's another comparison. We'll go ahead and think about that for a second. This is just shifting one element to another, an assignment, and this is just a decrement by 1. So, what do you want to consider? Oh, and then I forgot that at the end probably, where I actually need to set my temporary variable, right? Once I've got my temporary variable, I need to put it somewhere. Where do I put it? Oops. Increase the size there, and what was it? Yeah, a sub j. That's because that's where I stop off, and here it'll be t. Okay. But back to the correct pseudocode. Elementary operation. What would you go for? If it's a sorting algorithm, what are you doing at the core of your sorting algorithm? These two things, are they in order or out of order? Oh, they're out of order, so I need to swap them. Oh, they're in order. I stop my process and I insert the element where I need it to be. I'm going to vote for this right here, that comparison, right? So the comparison on line 4, right? The second one, not the first one, but does it matter? Go ahead and count them both. Now you've got two comparisons. And in the analysis that we did over here, right, instead of 1, you will have 2. Right? Who cares? At the end of the day, when you get a closed form solution of this, instead of 1/2, 1/2, we'll have 1 and 1, right? Ultimately, you'll ignore it anyway when you get down to this analysis in step 5. Okay? So let's just consider that one comparison on line 4. Whew. How many times is it, step 4, how many times, how many executions with respect to input size n? Now we're back similar to something, or similar to the linear search. Think about a sorted list already. 1, 2, 3, 4, 5, 6. Let's simulate, just briefly here, insertion sort on this list. We start over here. We make one comparison to see that 2 is where it needs to be. Then we move on. And now our temporary variable is 3. We make one comparison between 2 and 3 to see that 3 is where it needs to be. There's another comparison. We make another comparison between 3 and 4. Right? You see the pattern now? And the last one that we make is on 6 and 5 to see that 6 is where it needs to be. So if we got lucky and we tried to sort an already sorted list, insertion sort performs how well? Best case. There are going to be n minus 1 comparisons. Right. Can we assume the best case? Nope. So what's the worst case? So if it's already sorted, it's the best case. What do you think the worst case scenario would be? It's completely opposite. Let's simulate insertion sort now. So 6 sorted, no comparisons. 5, 5 and 6 need to be swapped. Once I've done that, that's one comparison. Okay. Now I will erase these and put them in order. This has now been sorted. 4. Oops. 4, I make one comparison to see that it needs to be before 6. I make 2 comparisons to see that it needs to be before 5. So, 2 comparisons there. Okay? And we end up with 4, 5, and 6. Right? And this is now sorted. Hopefully you start to see the pattern emerging here. Right? But if not, let's go with one more iteration. 3 is, there's 1 comparison, 2 comparisons, 3 comparisons to realize you need to put it at the front of the list. So, 3 comparisons, and now we have 3, 4, 5, and 6, and this is now sorted. Without me rewriting everything, predict how many comparisons to put 2 where it needs to be? 4. How many comparisons to put 1 where it needs to be? 5. That looks familiar yet again. 1 plus 2 plus 3 plus 4 plus 5. Or in general, if there were n elements here, it would be exactly that guy's formula. That's going to be n times n minus 1 over 2. Sorry, n plus 1. There we go. You're right. Right. In other words, if I expand it out again, it's going to be order n squared. Right? All right, well, best case, worst case. What about average case? You're not going to be lucky every time and not have to shift anything. You're not going to be unlucky every time and have to compare it to everything to put it all the way down, right? So what you can actually do, and I'm not going to do it since it's a little bit more involved, but it is in my Computer Science 1 book if you want to check it out, the full analysis. Basically, each iteration, you can expect on average to make I over 2 comparisons. Right? So here's the scenario. You've got a sub I, and you need to insert it where it needs to be somewhere. Okay? Well, if it's a sub I, that means that how many elements do you have over here? 1 through a sub I, or I minus 1. Right? And you're trying to put I where it needs to be. On average, you only have to look at half of them. And again, it's more complicated than this because you have to think about a probability distribution on all possible configurations, et cetera, et cetera. But you can think of, like, in worst case, you only need to make 1. Or, sorry, best case, you only need to make 1. Worst case, you need to make I minus 1. So if you just take the naive approach and think about it on average, somewhere in between, I minus 1 divided by 2. Right? Now you're doing this how many times? You're doing this n minus 1 times. Right? So when you do this, you end up summing a bunch of fractions. Just to simplify it, I'm going to take out that minus 1. Just make it bigger. And I runs from 2 up to n. Right? Remember, that's the outer for loop there? Right, it goes from 2 up to n. So what is this? This 2 can simply come out front because it's a summation. 1/2. I equals 2 up to n of I. And now we can invoke that guy's formula, right? And that's going to be 1/2 n times n minus 1, n plus 1. Now we're not starting out at 1 here, so we would have minus 1 implicitly. Again, I don't care about that, right? I'm just giving you the idea. Right? Ultimately, what value are we going to have out front here? 1/4 n plus 1/4, sorry, n squared, quarter n. Writing it all wrong there. And when you ignore lower order terms, when you ignore the constant sitting out front here, you still have a quadratic algorithm, right? But I show this to you for a very good reason. That 1/2 in practice, with the 1/2 versus 1/4, right? With selection sort, you had, where were we? Come on. With selection sort, you have this 1/2 sitting out front. With insertion sort, you have this 1/4 sitting out front. Now put on your engineering hat and ask yourself, is there a difference? Absolutely. In practice, insertion sort is much better than selection sort. You can expect on average to do half as much work, right? Half as much work is not an asymptotically fewer work. It's just it's still going to grow quadratically. You have an input size of 10 million. You go up to 100 million. That's going to be 100 times as slow. But that thing sitting out front now makes a difference when you're thinking about engineering yeah, and actual implementation issues, right? So if you were given the choice between these two algorithms and you put on your mathematician's, computer scientist hat and said, is there a difference? Nope, no difference, they're both quadratic. Right? But if you put on your engineering hat and say, oh yeah, there's a difference there, I'm going to use insertion sort over selection sort. But of course, in practice, you don't use either. What do you use? Quick sort. There's also something else that we'll look at is merge sort. Right? And we'll mention but not cover Tim sort. That guy. It was developed in Python, and it's now the default sorting algorithm in Java. Right? These are all n log n sorting algorithms. Much better than n squared here. Right? We'll cover these next time, but even better in practice. Yes, if you were to write your own sorting algorithms, you would want to look at this arena. But do you want to write your own sorting algorithms? In practice? Nope. Use a library. Right? Okay. So we'll continue. No questions online here. Looks like we had a really good stream the entire time, and it never slowed down once. So that's pretty cool. I'm going to be able to use my iPad from now on. All right. Have a good weekend.